Everyone, welcome to a very interesting talk today on the drivers and impact of melting of Himalayan Glacier by one of our alumni, Professor Indra Sekhar from Indian Institute of Technology in Kanpur. Professor Sen did his PhD at FIU under Professor Gautam Sen when he was studying xenoliths from the Hawaiian volcanoes. But after doing his PhD in 2010, he moved on to the Woodsole Oceanographic Institute. And from deep mantle, he moved his studies to isotopic studies and modeling of aerosols. And after his postdoc there, in 2013, he moved on to the Indian Institute of Technology, and he's an associate professor there now. But other than that, he has been changed his focus a lot from looking at hard mantle rocks to environmental problems, as you'll see in today's his talk today. He's done a lot of work on the geochemistry and path of pollutions in water bodies, something very similar to our Everglades, for example, tracing those things and do geochemical modeling. In India, he has received a whole bunch of awards, including the Young Scientist Award there, and in path for many more awards there. And he's also editor of part of editorial board of 3 international journals, which are Geophysical Research Letters and the Vedozone Science, and also Environmental Science and Technology. So I think his field now overlaps more with our environmental studies side than the geological side. So without much ado, I'll invite Indra to give his talk.
Thanks, Neptune, and firstly, welcome to the talk. And it feels so nice to be back here. I can see a lot of my professors, Steve there, Dean there, with whom I have interacted now. Being just joined at that time when I was graduating. Yes, I think he's correct that I moved from my PhD was looking into the core mantle interaction, core crustal interaction, and then everyone says that from that temperature domain, I actually moved into the high altitude Himalayas, looking at how the glacier melts, why it's melting, what are the pathways, and of course, a lot of pollution transfer. So on the backdrop, what you can see is a glacier called Drang Drung Glacier. It's in the Ladakh region, the northwestern part of the Himalayas. And you can see standing here, and as all of you are aware, Himalaya is it has a lot of significance for the Indian subcontinent. And the primary one, it has a lot of ice mass stored there, which actually melts. And there are many large rivers that flows down through it. So starting.
Try.
Yeah. So all of you are aware of the Himalaya. Before I go into the research domain of the Himalayan, Himalayan research side, let me also draw you some interesting fact about the Himalayas. Of course, it has some of the highest peak of the world, with Mount Everest standing at around 8,800 meters above the mean sea level. We have some of the finest tea, the Darjeeling tea, that is very famous. We have the Royal Bengal tigers in the foothold. Of course, really large river system, particularly the Ganga and the Brahmaputra, which actually makes up in Bangladesh to create the Padma River, which has the largest discharge of fresh water into the ocean, and a lot of work has been done out there. It has a lot of glaciers, as well as some of the highest and most dangerous motorable road. This is a little bit off now. There is one more pass, which is around 19,500 feet altitude that has been recently opened. So yeah, and of course, one horn rhino is also famous. So given this backdrop, let me talk about the Himalaya. Why we bother. As I said, that there is a lot of glacial mass. Of course, there are many other reasons. It acts as a barrier of the southwest monsoon wind, so that it does not cross. We get a lot of rainfall. But most importantly, I will only focus on the hydrology part of it, that it has a lot of ice mass which melts and produce river. And of course, the things are not that great. If you look at the temperature, there is almost 1 degree rise in temperature over the last 50 years. extreme rainfall events, the number of extreme rainfall events has gone down. And when I say extreme rainfall event, it means like there's a huge volume of rainfall over a very short duration, which creates a lot of hydrological disaster, including flash flood and so on. Glacial lake outburst floods, which are also, it comes into news quite often that since the glaciers are melting, there are being, really large water reservoirs sitting on top at this high altitude around like 8,000 meters, 7,500 meters. And somehow these are all naturally dammed through moraines and all. So once they break, just imagine there is a tank of water which actually, it breaks and water pours down, swiping whatever, is there on your path. So from temperature, from melting, these are some pressing issues that our country and particularly that Indian subcontinent region is facing. So it is important for us to kind of look into I think this is
Should be. Try it again.
Yeah. So you don't need to do a lot of science, just looking at images also is very clear. So for example, if you look at here, the 1974, 1994, 1998, 2010, and I am going into the high altitude field over the last 10 years. And even in the last 10 years, you will see the difference, how the snout has migrated towards higher elevation. Of course, the snout migrated does not mean that the glacier has lost overall masses, but actually visually there are a lot of change. So it is estimated that the entire Ganga Indus Brahmaputra basin has almost 23.7 gigaton of glacial mass that they are losing every year. And just to give you an estimate, if you look at that, the Empire State Building, 0.0001 gigaton of this blue sphere will bury that entire 443 meter tall building. So just imagine the quantum of the volume of ice that is stored, which is melting at a faster rate. So how much? So if you look at the worldwide estimates, you have 153 into 10 to the power 3, kilometer cube of glacier that is stored, and almost 8 to 10% is there in the Himalaya itself. And if they all melt, almost 519 river Ganga will flow. So imagine the scale. If we melt all those glaciers, there would be 19 new rivers that would flood the entire northern India. And it is the same scenario is overall. If you look at the Indus Basin, how the glacier has changed, the glacier area is projected to change in 2050. Ganga, Brahmaputra, the Southeast Asia is even more severe. Look at Salween and look at Mekong. It is expected that there would be a 50% shrinkage in the glaciarized basin. So given that backdrop, I think when I moved back to India, I started research on the Himalayan domain, and it's almost now been 14 years that we are working on it. So I tried to stitch a story together of all the dissertation that has been produced from my lab. So I will only talk about few key things that the first question that I would try to address is what are the additional drivers of why the Himalayan glaciers are melting? And I emphasize the word additional because we all know that the temperature is rising and they are melting. But here we looked into impurities in glacial ice and how they can assist in melting. So in terms of pollution. So that's why the term additional, of course, it has to do with the surface impurities in the form of black colored particle. In atmospheric community, that what the word they use black soot, or geochemist we use black carbon, whatever the way you name it, it is fine. So that their role, that how much it is there, where are they sourced from? Is it the fossil fuel soot or it is the biomass derived black carbon particle? So that's what we looked at. And then the second question is how they are transported. What are the pathways? What are the mechanisms? How they are reaching there? So that is the second question. And the third aspect, if they are melting the glacier, how that will impact the river flow. And that's where we have, my group has done extensive work in isotope hydrology, where we looked into stable isotopes and other tracers, conservative tracers to look into where are the water sources that is coming from. And then I would kind of, this is a very new niche area that we have started. We are trying to connect that the role of Himalayan orogeny into the CO2 cycle, the deep CO2, the geological CO2 cycle, that what we will talk about. And then how we are, my lab is actually we are doing a lot of translational research using geochemical principles. We are developing products, we are developing technology so that it can be used, and these are all related to the water sector. So this is kind of offbeat. So the first four is more like fundamental science, and the last one is more like if you call this applied, it is really applied. We are actually testing it in the ground. We are trying to improve many ways. That's what we'll talk about. So I think I thought that many of you would be from very different background, but I'm an isotope geochemist by training, and I used long-lived radiogenic isotopes. That's what I did in my graduate school days here. In postdoc, just the domains have changed from core to mantle to crust to atmosphere and then to glaciers. But ultimately, the toolkit is the same. It is isotopes. Just to give you a brief understanding, you have a parent which decays and the daughter, increases. And we have a single fundamental equation with which we can, age date, or we can use them as a tracer. The few that what we have used in this study is the samarium neodymium isotopic systematics, the lead isotopic systematics. So the only thing is I would kind of try to draw is that they have extremely big half-life. Half-life is the time frame it takes from the parent to go to a half of its amount. So the good thing about environmental tracking, environmental processes is the isotopic ratios don't change, because these are fairly young, young geological scale processes. So we are not looking into hard rock evaluation where it has through time integrated, they have decayed. So all the processes that if you look into aerosol transport into the Himalaya, if you look into soil forming processes, if you release looking into trying to track the fate of the contaminants in the aqueous system, their systems don't change, because the only way to change is through time delay. These are fairly, from time scale point of view, these are fairly new, so their values are constant. So these can be treated as a conservative tracer, all of them. And the other tracers that I use, that I have a lot of expertise, this I also have developed several methods when I was in Woodsole, looking into the rhenium osmium systematics that is now widely used in oil industry. And that's how I started with, because I was also working in the oil industry a bit. So looking at 187 rhenium decays to 187 osmium. Again, the take-home message is the same. These have very long half-lives. So the processes that we are trying to track today, particularly on the environmental processes, they will not be affected, because the environmental processes, the time frame that we are looking at is fairly young. So they will not change. So these can be treated and conservative tracer. And the beauty of the rhenium osmium isotopic systematic is they have a very dynamic, large dynamic range. When we look into samarium neodymium, you're looking at the third decimal place change in a number. So you really need high precision measurements. But for osmium, if you look at, I have given you the range. Say a tertiary coal will have a 0.2, a black shell will have 1 to 1.6. So these are some of the range. So we use them to track processes, and these are used, very well used in tracking different Earth superficial processes. That's what we focus. The other tracer that what we widely use is carbon isotopes. I think many of you are more familiar with the carbon isotopes. The difference between the radiogenic and the carbon isotopes is the carbon isotopes fractionate because of biological processes, physical processes, which the radiogenic isotopes don't. So here we would mostly be focused on the carbon isotopes that I think all of you are aware, but I will talk about something more than carbon isotopes when we actually get into the slides. But the idea is again same. The lighter isotopes prefer some phase, so they fractionate, and we can look into them and to identify processes. And the final thing what we have looked into is the 14 carbon. 14 carbon is, as you all are aware of, that they are used in age dating. So here, if you look at the modern organic carbon, these are the CO2 sink, fossil organic carbon, CO2 source, the soil is the mix. And then after all, they have the particulate organic carbon, dissolved organic carbon. And then we will come into it when we actually look into the problem statements. So now going back to my first question, that what are the additional drivers that are melting the Himalayan glacier? And here, of course, there can be multiple parameters. Here we have only looked into surface impurities. And when I say surface impurities, these are mostly black colored particles which are there on the surface of the black color particle. They are there on the surface of the glacier, and as black will absorb more heat, and usually they melt the glacier. So the idea was to look into that. Where are these black carbon particles or soot or fossil fuel residues, however you term it, they are coming from? And that's how we kind of started this research. Yeah, so of course, working in the high altitude Himalaya is a lot of fun. This is very different that if you work on the Alps or maybe here as well, where you can easily reach up to these high altitude sites. So for example, here we looked into one of these glaciers called the Chota Shigbi Glacier. It is a very clean glacier, and when I say clean glacier, means that the debris cover is very low. Usually most of the glacier is covered with a thick debris, brown color rock particles. So it is very clean. It has only 3.4% debris covered on the ice. So the white ice is exposed. And if you look at that, if you actually take a walk, you will see this black color potholes. And these are all some kind of heat absorbing particle to us, because it will absorb heat. So the idea was to look at where they are. Yeah, so the idea was to look into the origin and sources of this black colored particle, which we called is at Pryakonite hole in this glacier. So if you look at the sampling sites, we went up to almost like 5,500 meter above main level. So it's not a easy task. So our base camp was at around 3,500 meter. From the base camp, we have a high camp at 4,000 meter, and sampling was done because you can only get without oxygen. So you can only go up, spend a couple of hours, maybe 30 to 45 minutes, grab your sample and come back. So this is the picture of our base camp. From there, there's a high camp and so on. So we sampled throughout this glacier. It's a very clean glacier, and the idea was to look into the source of this particle. Now, whenever we do a source tracking, the other thing we have to know is the probable source end members. So then only you will be able to fingerprint them from where they are coming from. So of course, the most possible source is some aeolian dust transport, some black soot transport. So what we did is we also looked into the aerosol fraction, PM10. If you are working in the atmospheric community, it's a particulate matter of 10 micron diameter or less. So we sampled in 2 locations. The site was the Herschel site is a representative of a really pristine site where there is no major industrial activity in a 100-kilometer radius around it. It's almost a forest in a high altitude Himalaya. That's almost the baseline aerosol site. And then of course we started sampling in Kanpur, the city I am from, my institute is from, which is a heavily industrialist town. So this is the dirtiest you can get. So we had the entire spectrum from the cleanest to the dirtiest you can think of. And then also we looked into engine exhaust. So we have an engine lab where what we did, they have this huge engine exhaust setup. So we put our particulate matter at the tailpipe of the car and vehicle, and we ran the engine in different RPM, and we collected them. So these are and then of course we measured the coal samples, which actually when burned, coal fly ash is produced, which can be transported. So the idea was to kind of look into all possible sources, because these are the possible carbon releasing sources into the atmosphere, so that we can track back that whether it is a coal burning, which is the issue, or it is the engine, the diesel car that is being burned to run vehicles, that is the issue. So we tried to track tried to quantify the end members as well. We measured the sample so that the fingerprinting becomes easy, and that this approach should be for any tracing work that anyone of you does. You kind of have to have a good understanding on the end members. And then what we looked into the rhenium osmium layered measure and trace elements and the organic carbon nitrogen, and of course we integrated with air mass back trajectory and high split and all those things. So if I look into the data, of course, there's a lot of geochemical data. I can talk for endless hours on this. But the idea was most of the triconite are those black colored holes where these black particles are, we saw. If you look at their trace element pattern, it is very similar to the moraines. Moraines are when a glacier moves, there are a lot of rocks on the side of it. So you have the bulk moraine, which are large rocks, and you have the fine moraines because it also produces since the glacier is a dynamic thing, it moves. Once it moves, it really fine colored, fine particles. So fine moraine are those fine surrounding rock, and bulk moraine is those large rocks. So if you look at the triconite, the dust chemistry, the triconite hole chemistry was very similar. And if you look at the osmium, there were, if you look at the transits from low altitude to high altitude, there was some variation. But the take-home message from this slide was it resembled very similar to the local rocks, and that's what you would expect because the majority of the dust would come from surrounding rock, and these are dusty area because a lot of the physical weathering rate is so intense in this region. You expect to produce a lot of dust. So that is what we saw. And then, as an isotope geochemist, we run all these fancy, not very fancy, just simple isotope mixing models. But the take-home message, what we saw that most of them were local rock material. And I'm talking about the overall chemistry of the triconite hole particles that what we collected. 97% was local moraine, and this is only terms of osmium. And rest was, so of course, osmium, I just give you a quick example. Osmium is also released from catalytic converters in car because all our catalytic converters are coated with platinum palladium. So when a vehicle moves, it releases them. So PGE, platinum group element contamination, usually is tracked back to vehicles movement. So we did not see any sign of vehicle derived material reaching to those high altitude sites through aerosol transport mechanism. So this was the major findings that have been published in last 3 years ago in 2020 and 2021. And this is the story of osmium. And now we decided to look into the source of carbon because we know the black color material is coming from the carbon. And that's what we started looking into carbon. So the entire study is actually based on three samples, I would say. Now, these measurements, what we did, so we are all aware of the bulk rock analysis, where we take a bulk rock, we make, we degas and we measure them. So this is a very different kind of measurement where we looked into one sample and then we heated it up. Now, once you heat a rock up, it will oxidize and it would produce CO2 at different temperature interval. So we trapped all those particular CO2 that has been generated at specific interval, and we did a 13 carbon and 14 carbon measurement of those fractions. So one sample was split into 10 samples because that will give you a lot of more additional information that will usually be lost when you're looking at bulk measurements. And this technique was developed at Woodsole, that what we followed. It is called the ramped pyrolysis oxidation. It is a 13 carbon, 14 carbon measurement, but looking into individual splits. So this is what it shows. You take the rock, your bulk, one sample. So you have 1, 2, 3, 4, 5 samples actually. So the entire EST paper was based on data from 5 samples, but 5 was split into 5 RP1, RP2, RP3 individual temperature fraction. So first one was lower temperature, RP2 was higher, RP3, RP4, and RP5. So is it clear that this is a little different from the bulk rock measurement? It is almost, you can say, compound specific measurement, but really not looking at compound, looking at each individual fraction that has been generated at a temperature frame. So that's what we do. So this is the thermogram if you look at. Of course, that is what you would, K is the Kanpur aerosol. As I said, Kanpur is an industrial city. So if you see, their peak of CO2 being produced is around 400 to 500 degrees Celsius. But the rest are all around 300 degrees Celsius. So clearly it is visible that C9 at the CR stands for the cryogenites, TF is the bulk mordant, and this K and H are the aerosols. So all of them are more or less similar thermograms, apart from your Kanpur aerosol, because this was the odd sample out, because we collected in the industrial city, and they are very similar. So from there, what we did is we tried to calculate the activation energy of each fraction. And this is the RPO fraction. Just to brief you, it is the fraction modern. So out of those carbon that we measure, how much is modern and how much is old? That's what we do with 14 carbon dating. So old black carbon particle will have a modern fraction 0, because it's all old, and modern means the one which is fixed now today because of degradation and all, will have a fraction of 1. And these are the activation energy, because activation energy can be calculated based on the bond strength, because we are releasing CO2 at different time frame. So based on that, we can calculate at what level. So of course, if you look at this, these are the Kanpur aerosols, these are the Herschel aerosols. Herschel is a pristine site. So all the carbon there should be, recent origin. These are biomass derived carbon from local places, and that's what exactly we see. These are ages in kilo years. So these are all very recently fixed organic carbon. But compared to Kanpur aerosols, you see we have 7 kilo year. The carbons are really aged, because it basically falls in a mixing line between modern and somewhere in old. And OC Petro, which is the one which is derived from petrogenetic, the rock derived carbon, these are again very resistant. These are, so they all will have very high activation energy. So similarly, when we plotted the both the samples, the cryogenic sample, we had 2 samples, right, of different fractions. So we clearly see that they are all, mostly they are young, 80% of them, but there are few of them which are old, 6.22 kilo years, 4.01 kilo year. So they are young, that means clearly these are biomass derived carbon which are locally derived. They have nothing to do with fossil fuel, otherwise their modern fraction would be much lower. But see, we see something here, because there are also a lot of rock derived carbon. So this is actually falls in a mixing line between the rock derived carbon and the modern carbon. This is very different from this trajectory, which is fossil fuel derived. So we did a calculation of mixing calculation, and what we find that again, the carbon that what we saw, the black color, the soot that was present in the Himalayas, it is nothing to do with the fossil fuel source. It has been all organic carbon from biomass, which has been recently fixed. So it is not that they are being transported from faraway region and it is polluting, at least not in our case. And this study actually contradicted the recent findings where there are other regions where they found significant fossil fuel signature on the Himalayan glaciers, 50% of fossil fuel signature in the Himalayan glacier. And this is important, because if there is so much fossil fuel carbon going there, it will melt the glacier at a much faster rate. So then we looked, we collaborated with atmospheric chemists, and what we found that it is possible. The only reason it is possible, because the site where we are in, it actually encompasses a different sector. But these sites where 50% fossil fuel inputs were found, it actually captures the entire northern part of the Indo-Gangetic plain, where the heavy industries are situated. So we are not saying that they are right or we are right. It is one possibility that our capture area is little bit different than the capture area of the previous studies. But said so, our one is more compound specific, so we have a much better control. Otherwise, if you look at this data, I'll just show you. If you did not do your individual fraction specific measurement, if you took one bulk, of course, if you look at the blue color one, 1, 2, 3, 4, 5, because we had 5 fraction, right? RP1 to RP5. If you actually have measured the bulk rock, you would have got one single value at 1.9 or 1.2, because it would be one single measurement of the mixture. And then, of course, you will claim, look, this carbon that we found here is old, aged. But that's not the case. You have also so many fractions sitting here. It is only that one fraction which actually will bring the value down into an age. So these are much better in terms of getting the entire spectrum of the story rather than going for a bulk measurement of your soil or of your rock samples. So said so, then our second aspect was to look at that, okay, we know these are biomass derived carbon, but from where they originate? Are they even, because there is a lot of biomass burning which happens in the Indian subcontinent. There is a lot of forest fire that is happening. So is it this biomass derived carbon coming from local region, or they are being, coming from far away region? So for that, we actually did an extensive sampling of the entire catchment area from where air mass can go in. We looked into coal samples, obviously the ash, dry wood, wood, Indian coal. Again, the idea was to constrain the N members, because if you don't have a good handle on your N members, how can you track? Because in order to do a fingerprinting study, what do you have to fingerprint? You need to know the N member specimen. So we did one of the extensive N member sampling, and we ran a time series station where we collected weekly data at a very high altitude location. I don't want to go into a lot of technical data, but what was striking was, if you look at the 206, 204 data, what was striking that throughout the year it is more or less the same, but only in winter the values are different. Same with your other all tracer. So clearly winter was something little bit different than rest of the year. In the rest of the year, winter is defined from November to February. Rest of the year, it was more or less stagnant, but winter was something off. And, because of the time, I'm not getting into it, but again, this is also clear. This is a good plot that we have plotted 206, 204 lead over epsilon 90 mm. It's a way to represent 90 mm isotope data. You see the winter have some sort of trajectory. That means they are in a relationship, the neodymium and the lead, but the non-winter are scattered.
When is the rainy season?
Yes, that's a good point. So if we were expecting something off, that would have been the monsoon season, this part. If something was has to be off, that has been the monsoon, because monsoon also acts as a cleansing agent. It would have been removed all lead from the atmosphere. So what I was expecting that this trend would be constant throughout, but the monsoon signal would be different. But that was not the case. It was constant throughout, but the winter was off. So, and that was kind of really fascinating, and we were unable to find what was the reason. There are multiple reasons, and I'm not getting into all these details. But the first, of course, obvious, and then we actually did a geochemical classification. That's the same thing. It shows that the Indian coal contribution decreased in winter and the local crust composition increased. So in winter sample, you have more local dust coming in than the transport in the other season. So now the of course question is why? That why you have winter so different than the rest of the year? So the first explanation would be, okay, let's look at the wind direction. Maybe the wind directions are different. Maybe it's tapping some other source. Maybe the wind speed, if the wind speed is different, it is only, taking up a particular size fraction. So all these possibilities, there can be multiple possibilities, but we did not find any relationship. And then I have to kind of take help of my atmospheric colleague. And what we figured out, it has to do with the planetary boundary layer height. I think Ping can be a better person to explain that. But how we explain this, I will give you a simple scenario. in summer, what happens is the planetary boundary layer height is much higher. And as a result, because the heat, Indian summer continent, in the summer in India is quite brutal. We have temperature around like 110, 115 Fahrenheit throughout the summer season. And because of that, the planetary boundary layer height goes much higher, which allows all the contaminants to actually reach up to there. But in winter, your planetary boundary layer height is much lower, which actually caps the contaminant at a regional local level. So if you look at this, the red color, everything and everything remains transport mechanism, which is controlled by the planetary boundary height. With winter, you have, because it is lower, everything is trapped here. And in summer, the planetary boundary layer goes high. It is just the lead of a chimney. If the lead is higher, everything goes higher. If the lead is lower, it is capped. And this is kind of brutal in the sense that summer, the temperature are the highest, when the melting rates are the highest. And on top of that, you are actually removing all the pollutants to the high altitude, even this black color, whatever is reaching there, which will enhance the melting. And this is also one of the obvious reasons that why we see so much haze and air pollution in the winter time, because the pollutants cannot escape. So they all rotate. Summers are, from pollution level, it is very clean in India because it's so hot that everything escapes. But in winter, the planetary boundary layer height is low, so nothing can escape. So we came up with this theory. And so we know that the biomass are coming from local region, and we also see that the dust transport is controlled by atmospheric planetary boundary layer height. And now I think this is more relevant to many of you, what you're doing here. We work a lot on isotope hydrology in order to understand the contribution of snow melt, ice melt, groundwater, you name it, and we can do it. We use chlorine, we use sodium as conservative tracer. The concept is very simple. If you look at RGB, and in the center you have the mixture. So if you know the RGB composition of this mixture, you can calculate the red component, green component, and blue component. So similarly, this has been done with isotopic measurement. I think I have introduced you how it works. We are working on the Nubra Valley, the Indus Valley, the Alaknanda Valley, and looking into the ice melt water in the streams, the snow melt water in the stream, the rain amount, mostly these two rivers basin, the Indus and the Ganga. And what we came up with, because of the time, I'm not going into technical detail. We have almost 5 to 6 journal of hydrology paper on different aspects of developing the model. Say, for example, Zanskar, we have worked in Puga, we have worked in Indus, which is very different from the central Himalayan region, because as you can see, these are low relief, extremely lower temperature, low precipitation, lot of geothermal activity. And in comparison to the Bhagirathi Alaknanda basin, where you have high relief, high temperature, higher precipitation. So of course, their runoff, their melt contribution would be very different. So that is what I was talking about. If you look at the distance of the river and the elevation profile, these are much shallower steep compared to this. So runoff would be much faster on this. The response time would be much quicker. So, these are, even in India, there are so, from climate point of view, so different, from hydrology point of view, they are different. And that's what we are looking into. The idea is very simple. We try to first establish conservative tracer, which can be DXS, which can be oxygen isotope. Usually we don't use oxygen and hydrogen because they have a relationship. So you get into an autocorrelation problem. So we try to establish different tracers. And the idea is to make an hydrograph split into several components. So it is all about. And this is what we found, again, published by my student in geochemical perspective letters. These are the mass losses which are happening every year in these rivers basins: Indus, Ganga, Salvin, Brahmaputra out here. And here we have compiled all the data. So it's quite dynamic. If you look at these are the 74 to 104 degree east latitude, and how the melt rates are changing as per even elevation. So with elevation, different rates. So this was one major finding. So I will quickly go to the end part of it, that what we have recently started working. We are now looking into the role of deep mantle in atmospheric chemistry, in the sense that when you have subduction, when you have any metamorphic reaction, any reaction produce CO2, and this CO2 comes up to the surface in either in diffuse state, any soil. If you put a soil chamber, if you make a soil chamber experiment, apart from that, the CO2 released from roots and all, there are also a lot of CO2 which comes from the subsurface, because if you have carbonates with high temperature, they will decarbonation reaction and CO2 comes up. But the most common thing what you see here in hot springs, I don't know whether there are hot springs here nearby, but hot springs are a direct conduit of material from deep earth to come up, because usually through fault plane, the meteorite water circulate, picks up volatiles, and then come up, and then they get depressurized, and it releases CO2. So that's what we are working on right now. If you look at the mantle, 3 helium and the CO2 source, then it comes up and then it goes to decompression and releases CO2 in the atmosphere. So what are we doing? What we do is we do Rayleigh fractionation model. Again, this is, I think it's quite complicated. So how it works is we collect hot spring water. Now, hot spring water, we measured the delta 13 DIC, which is the isotopic composition of the carbon in the water samples. So if it has gone fractionation, of course it would. So the air would be of a different isotopic composition than the residual water. So based on that Rayleigh fractionation model, we try to estimate that how much CO2 has been degassed from each hot springs, and looking at the geothermal discharge, we can quantify that what is the CO2 is being released from each hot spring at that time frame. And then on top of that, we kind of use mixing model to kind of tease apart that this CO2, where is it coming from? Is it local aqueous carbonate dissolution, or it is deep mantle? And so this is, for example, if you look at this, here your delta 13C CO2 composition, which is depleted. Here is your delta 13C DIC composition, because the heavier isotope stays in the water, the gases are much more lighter. So based on that, we can come up. So again, then what we did is we had our data, we had data from the published literature. So we mapped the entire CO2 that is being degassed from each hot spring in the entire Himalayan Hindu Kush region. And not only that, on top of that, we kind of data mine and look into the diffuse CO2 flux. And this is what it will look like. And then if we can, go and look into the discharge and everything, the take-home message was, we found that the CO2 degassing in the Himalayan orogeny is order of 10 to the power 11 mole per year. Just to give you an example, these are the natural CO2 emission, because most of the work has been done in volcanoes, where there is a connection between the deep earth from where CO2 comes up. And if you look at the mid-ocean, the continental rift, so they are of the almost similar order. So it's quite a big looking into the geological carbon cycle. Again, I'm not talking about the anthropogenic CO2 emission, which is in the order of petagram. This is all about in the terms of geological carbon cycle. But this flux is still missing in the entire geological carbon cycle modeling. So this is the first flux we are actually trying to put forward. And I'm sure it will be published soon, because it is under the second round of revision in Earth and Planetary Science letters. And these are then we also use the mixing model. So this is our contribution into the entire geological carbon cycle, being between a balance between source and sink. These are the sink, which means it takes CO2, and these are the source, which means it releases CO2. So we are saying metamorphic CO2 degassing is a source to the, and this has to be accounted when we actually do a mass balance of the geological carbon cycle. So that is all about and the last part, which I will just briefly touch, is we are also on our group being in one of the most premium technological institute. We are surrounded by good engineers. So we started working on developing technology to kind of track pollutants. So a major problem with the research, what we have so far talked about, and which many of you are doing here, this is too high end, given the scale we have. We have in my state, in Uttar Pradesh, we have almost 5 lakh, which is 5 million water sources to track. So given that, we cannot employ field protocols like this at that scale. It is just nearly impossible. So the current practice, research practice, is to scale up. It's quite complex, requires skilled manpower, proper sampling protocol, correct vials, screening protocols, preservation protocols. Of course, it involves high-end equipment, no centralized data management scheme, expensive. So this is where we came up that, is there a way to kind of ease out this scaling up? Of course, we are not producing research scale data, but in order to do monitoring at a large level, you really don't need a 1% precise data to understand whether the source is good or what. You need bulk data. So how it works right now, all the research talk that you talked about, we go to the field, we have some probes which has to be clearly well calibrated before we use. Of course, they have limited parameters, DO, TDS, whatever you can, ORP, of course, expensive. And then we go to the field, then we package them with high-end sterilized vials, clean columns. And then finally it comes to the mass spec or IRMS or GCMS, whichever instrument you are working on. So we decided that, is there any way to kind of, and this is the problem statement, let me tell you. If you go to a state lab, their supply is way more than their actually analytical capability. If you go there, you will see things are lined up like this, like thousands and thousands of samples coming from all small district counties, and there is one central big lab which they cannot handle. So the opportunity here is, can this, and also you think that water is heavy. If you are sending 50,000 water samples, 1 liter, that is almost 50,000 kilograms. So we actually came up with this. This was based on the dry blood sampling technique, where you can extract contaminants from water in a dry format and ship it. We don't need the entire 1 liter. We only need an ion exchange resin which can capture your contaminants from your water, and then you ship it in a dry format. And our Indian Postal Service is one of the best postal service network. It reaches every village level. So rather than having the pain of taking water bottle, clean one, remove impurity, remove physical impurity, physical particles, why not we provide them some technology that can only take out the target contaminants, and then it is only 3 grams to 5 grams that you need to ship. So this is what we came up with, something called Clear Bottle. It has been patented right now, and we are actually scaling up. It is called cleansing, light, easy, and reusable. And everything has a meaning. Cleansing, why? Because if you're putting water, it is a collapsible bottle. There is nothing in it. It's not like a normal bottle. It can come up in my pocket. It can be your tea bag. The tea bag you put, it can be a same format. There are different formats of it. So how it works? You take this bottle's collapsible form. It has designated resins in it. You put 1 liter water, that is the maximum you can put. You can shake it. Any ion exchange reaction will take up something and will release something. You make sure it releases something which is not harmful, and you take up your target contaminants. Now that water which you now throw away, it has been cleaned because those contaminants has been already taken up by the resin, right? And now the resin, you ship it to us, we can again elute the resin, elute the contaminants from the resin. So we also get a measurement. And again, it goes back to get recycled in the field. So it is the innovation is, it's a purification as well as a monitoring on a single channel. From how we solve the sampling problem, we don't have to do filtration, then nothing has to be cleaned. Anyone can do it, fill water, shake it, done. And then we actually in the lab scale, we can do it. It can be stored for years because you are actually preserving the contaminants in dry format. There is no solution. If 50,000 of these bottles can actually fit inside, that you won't need a huge room to kind of save. So this is what we are working on right now, quite efficient in recovery and everything. And so the idea is simply, so from household level, you can just post it using your postal service to the direct laboratory. So you don't have to go through the entire supply chain of going there, going to the fields, shipping it to a district or county lab. From the county lab, if they don't have the equipment, it goes to a bigger lab. So the entire supply chain kind of gets shortened. Is a easier, smarter way to kind of ship. So I think I have taken up a lot of time. Just to, my brief take-home messages are, of course, there is negligible fossil fuel inputs were found in the glacier that we studied. I'm not saying that they are not there in the other, but at least the one we studied, there was no fossil fuel. We talk about a flip-flop scenario where winter season have, the high altitudes are less polluted because the planetary boundary layer caps the pollutant. So our plain areas are much more contaminated. And winter season, the winter season came twice. So the summer season, the pollutants easily go up. So that's how they are being transported. Isotope hydrology modeling tells us this is the actually ice melt that is actually melting every year in the Ganga, Brahmaputra, and the Indus. And from the Tibetan origin, the Himalayan Tibetan origin is also emitting 10 to the power 11 mole of CO2 per year, which is almost equivalent to a outgassing from continental drift. And combined water purification and water technology is not a dream. It can be done using some sort of ion exchange resin preservation protocol. So said so, I would like to thank. I am just the voice of all the students who have actually worked so hard. I'm just speaking on their behalf. My postdoc, who's now in associate professor in Chinese Academy of Sciences. Shomita, who actually did all the isotope hydrology work. Arijit, who actually did the mechanism of how particles reach. He's now a postdoc working with Alex Halliday in Lamont. And Sarwar is a postdoc fellow in Humboldt, now GFZ. He's the International Climate Protection Fellow. Nita just finished her PhD. She joined the lab in Rennes, France. So these are all their work, and I'm just saying, and of course, all the funding agencies that actually funded this research: the Ministry of Earth Science, Department of Science and Technology, Intel, some analysis. The RPO was done in Group Zone. And of course, we had USAIDs also then when I started my career. So thank you so much. And I would be happy to take questions. I have covered a lot of ground.
It's now open for questions.
Yeah.
So these candidates,
Trichonites, yes.
do you know like their longevity? So you measure what's in the black spots.
Yes.
But how is the amount of black spots across the surface changing? Because if you're constantly losing ice, you might imagine that the relative proportion of black spots increases. Or do they get covered up every year and then you get a new fresh white layer?
Yes. So these would be covered up every year with fresh.
I was muting to jump in.
Okay. All right. So this, of course, every year it will change. When in glaciology, there are two seasons. One is the ablation season, where everything melts, and the other is an accumulation season, where the glacier grows because of the winter snowfall. So in the winter, everything gets covered. And again, that winter snow mass will go away. So you will only get this exposure back in, say, May to June, when the surface snow layer has been completely melted. Now from May to say June, July, their size grows bigger and bigger because the surrounding area melts. And if there are more particles, they will actually flow through the small, tiny, water channels and actually gets accumulated in the hole. So with time, the hole goes bigger and bigger. But of course, it will be again covered up by next year. Again, the same cycle starts.
But do you notice if over time has there been an increase in the surface area of chondrites in May through June?
No. We have not looked into it, but it will be. So that's why the only time frame to actually collect a sample is between May to June. Yeah. Because the fresh snowpack has to melt. First, it has to melt, expose the bare ice, And this bare ice, will have large spots, like I have seen spots like this big, like small ones, which is under formation. These small ones will melt and all the particles will come and join and slowly, slowly they evolve. That's how a cryoconite hole evolves from a small needle size to a football size.
Do we have any questions from our international listeners?
Yes, we have a Zoom. You can unmute and go ahead and ask your question. Anybody on Zoom? Again, if you want to ask a question, just unmute and we should be able to hear you.
Yeah.
Yeah, it's nice talk and excellent work. So you mentioned that the boundary, the particle transport. I think the boundary height is only part of the reason. So I think the most important is the thermodynamic structure, because in the winter time you have very strong inversion to carpet. So if there's no mechanism to pump the air pollution out of the boundary into the free atmosphere. But in the summer it's different because you have a convection. Convection is the mechanism to pump the air pollution from boundary into the free atmosphere, and because the convection has an outflow, so you can transfer the very high.
Because of course the
Yeah.
heat flux is
Yeah.
so high, the convections are much more stronger in
So
summer.
the reason is because the inversion is different.
And
In the winter time it's much stronger.
Yes.
Basically.
so the pumping,
Yes.
the intensity of the pumping.
Exactly,
Yeah.
is that because of the convection in the summer.
Yes.
I was wondering why you not go through the ice and look at different seasonal layers. The reason I'm asking is because in the summer, I mean, from our basic intro earth science, we know about the Indian monsoon. So in the summer, the land is hot and there's a high pressure in the oceans, and it the wind blows from oceans toward the land, and eventually that pushes everything up on the environment. In the winter, the opposite thing happens. The wind blows from the mountains toward the ocean. So it takes all the soup to the ocean. So there should be some seasonal variation just because of that.
Okay, I think the question is why did not we core? Because we failed big time. Now, why we failed, I'll tell you a reason also. When I moved back, I was young. Now even I'm more young. But anyway, that's not the case. We had the core and everything. The one core that we used in Greenland and everywhere from coring perspective. So we purchased, we procured, we went up, we tried. Now, the problem with working with Himalayan Glacier and Greenland Glacier is, first of all, Greenland glaciers are a sheet. These are flat, and Himalayan Glacier or valley glaciers, steep. Now, first, number one, if you have to really do a drilling, you have to go around above 6,000 meter elevation, which is unless you are a trained professional mountaineer with oxygen cylinders, you cannot do it. So of course, we still tried to go up to 5,400 meter. But then what the problem is, if you're right on the borderline of the ELM, it's called the between the ablation and all, our glacier has a lot of moisture and water content. So when we started drilling, what it happens, you drill like 2 feet, now water rush in, and now it freezes immediately and then once it freezes, you cannot take the core out. So for that, you have to put some de-icing agent first so that our core don't get stuck. So it is way more complicated. So that's why as on date, and it is also the relief. Imagine with all these generator, high altitude cables, the barrels, the setup, it's quite difficult.
Yes, would the correct folks?
No, I'm not. But that has a lot of have been done on the other side, on the Tibet and the China side, because on that side it is more like a little bit more flatter, and then of course there are large institutions. They have like chopper or helicopter where you go and collect. In Indian side, it's very difficult. Many tried, yeah.
I have another question. You showed one of the slides, you showed the glaciers moving up, but you said that does not necessarily mean the shrink of the glacier mass. But if you look at the Kilimanjaro, they do shrink a lot. But in this case, do you see any kind of a record to show the glacier shrink? Himalaya?
Oh yeah, there have been multiple studies which shows that the glaciers are shrinking. What I meant is, if a valley glacier works like this, it has a big catchment area and there is a small snout. So the snout retreating, that doesn't mean that the glacier is losing mass overall. Maybe it's gaining mass on the catchment. So that's why people, when they say that, oh look, the snout has retreated. If there's a glaciologist in the community, they will say, look, the snout retreat doesn't mean anything because ultimately you're gaining mass in the high altitude. So that's why I made it a little bit clear that looking at the snout does not mean that the glacier has lost its mass. Of course, it is an indication that the snout is retreating, but not always true that the snout retreated, but it has gained certain amount in the high altitude area. Overall, the net mass balance is positive.
Is it because they have a lot of precipitation there, and then the free going to the altitude is so high, and then there's open into.
I think, yeah, well, I'm not a right expert to answer, but the entire mass balance, the community, mostly the glaciologist does mass balance, like, how much it's losing and how much it's gaining. Say, for example, I told you that 33 gigaton is lost every year, but I did not quantify how much is gaining every year. So that the community does, that is the net mass loss. This is a mass loss, but you're also gaining mass in the winter. So if you're getting 37 losing in the rivers every year, and you're gaining 38 gigaton in the winter, so still you're in a positive mass balance. Now, why some glaciers lose, some glaciers are gaining? Of course, very few glaciers in the Himalayan system is gaining. There is only glaciers in the Karakoram range, few of them which are maintaining status quo or gaining few percent, but overall there is a shrinkage. But that depends on the face of the glacier, which side it is facing, relief of the glacier, many components. But I think a glaciologist would be able to answer you more specific way.
Which three?
Few in Karakoram, I don't know.
Siachen and
I have no idea. Maybe, yeah.
I'm done.
Have time? So one of your, by the way, it's a great presentation. Thank you. One of your objectives is to identify the sources of this carbon. You're not able to measure the source from the other side of China, right?
Yeah.
I remember, back like 2 decades ago, in early 2000, they were trying to perfect the global climate certification model. One of the missing pieces was that aerosol coming from China and Indian subcontinent. And when they put that component, then they got much better projections, carbon. So there's a huge source coming from there. So without taking that into consideration, your measurement be complete.
Well, it is yes and no as both a way, because you see the Himalaya act as a wind barrier as well. So it is only the very high, again, that's why my understanding, I think Ping would be a better person to say, only the very high altitude transport can come in. But the majority of the air mass, even if you do a high speed modeling, it will all come from this side. There is no crossover from this side.
But I think for this case, I have to be very careful because in that latitude, the dominant wind is west.
Best, yeah.
So it's coming from the Indian toward the China. So, So you have to look at the halifax connections.
And the Tibetan side, you neither have forest nor have industry.
Yeah, and also like when I talk about the sources are fixed. It does not be defined by any political boundary. Like coal, we measured coal, Tertian coal, we measured carboniferous coal. Those coal samples are the same that will be burned in Pakistan or Afghanistan or China. It has nothing to do with the type of emission. So what I'm trying to say, some of the sources, the end members are fixed. They are not it's not that the tertiary coals are different composition globally. It is the same.
Dr. Sen,
Yes.
can I ask a question?
Yeah, sure.
My name is Bhattacharya. I am from India, Neptune's friend.
Okay.
I wanted to know whether you have considered Western disturbance in your calculations, contribution of dust or contribution of isotopes or anything? Because I think I saw some western disturbance line in your diagram, but have you considered that?
Well, there are two parts to it. When we looked into the cryoconites, cryoconite is it's a summation of whatever happened in the samples. If throughout the year there are storm events or extreme events or western disturbance or southwestern monsoon, whatever, so it is not really looking into the impact of these on those cryoconite. It is actually tracking the source, where are they coming from. So it is kind of irrelevant for on that point of view. Now, talking about the Herschel, where we actually measured the time series, again, it was weekly sample, which actually covered whatever atmospheric circulation which happened over that year. So yes, it is included. So I did not exactly get it, that what you meant by the impact of western disturbance, because it's a time series data, weekly time series data. So if there was any impact on the transport, we would have seen in isotopic signature.
But I think in the deuterium excess, the western disturbance would increase the deuterium excess to a very large extent.
Yes, you're correct. Yeah.
And therefore, I would look for the signal in the deuterium excess, because I have done some measurement in the Bias River and published in hydrological processes, where I showed that there is some finite contribution of western disturbance if you consider the isotopes. I don't know much about the particles and other, other things.
Yeah. No, deuterium is would be a good crustal tracer. So anything because there is no samarium, niobium anthropogenic sources. It is mostly the crust which contributes. So we saw a very minor change in the winter time. Yes, there were more towards crustal in the winter time, which were also very similar to our lead story. The lead also was more towards crustal.
Okay, thank you very much.
Yeah.
We are done, then we can go for lunch.
All right.
Thank you very much for that very interesting talk.
Take care, Zoom room.
Several projects.
We are slightly close to the Vietnamese stress across in the morning.
Waterman,